Let's walk through the steps of graphing a quadratic function by hand, utilizing all of those important characteristics of the quadratic function in an effort to help us create a comprehensive graph. You'll see that this quadratic function is already written in standard form. So the first thing that I should do is try to identify a, b, and c. A is the coefficient of the quadratic term, b is the coefficient of the linear term, and c is the constant. We're going to need all of those numbers in order to create the full image of the quadratic equation. Always a good idea to start first with the vertex. So remember, our vertex formula is negative b over 2a, negative 8 over 2 times 1, which is negative 4. So we should expect our vertex to be at the x-coordinate of negative 4. That also tells us that our axis of symmetry is going to be at x is equal to negative 4. So we can draw that imaginary vertical line that we're going to use to help create our mirror image on both sides. Now, using this negative 4, we can go back to the original function and determine the y-coordinate for the vertex. Everywhere we see an x, we substitute out the x and put a negative 4 in its place. And a careful bit of arithmetic, you can check that we should get negative 9, meaning that our vertex is going to be at the point negative 4, negative 9. Once we have the vertex, it's a matter of finding other specific points that could help us when we want to draw the graph. The first pursuit should be the x-intercepts. Going back to the original equation, we'll find our x-intercepts by setting our equation equal to 0. Now, there will be situations where you'll need to break out the quadratic formula in an effort to solve this. The quadratic formula may result in no real solutions. It may give you that there's only one solution, which you would have probably already detected because the vertex would land on the x-axis, or you could just get two regular real solutions. In this case, it's a little bit easier to jump right than to jump right to the quadratic formula. A little bit of careful looking, we see that our polynomial is factorable, which gives us two solutions thanks to the zero product property. X is equal to negative 7 and x is equal to negative 1. Now, the nice part about negative 7 and negative 1 is we can see that continued symmetry. Negative 7 is still 3 units away from the axis of symmetry, and so is negative 1. So it's not as if we got the axis of symmetry in a particular place and then the roots were somewhere else, like way over here. Those roots are actually a nice confirmation of the axis of symmetry because we know that the axis of symmetry needs to be halfway between them. Lastly, we're going to look one more time at our equation, and this time we're going to focus entirely on the c. That gives us our y-intercept. So because this equation is written in standard form, x equaling 0 will wipe out the quadratic and the linear terms, and we get a y-intercept at 0, 7. Now, we would normally be able to draw a pretty good sketch of the right-hand side of this parabola. So starting down here at the vertex, I know I'm going to have to travel through negative 1, and I know I'm negative 1, 0, and I know I'm going to have to travel through 0, 7. But the left-hand side is going to be a little bit dicier. Yeah, I want it to mirror, but I'm not positive that I have just enough points to make it mirror the way that I want to. And that's where the y-intercept comes into play, because just like the x-intercepts were each 3 units from the axis of symmetry, the y-intercept and its mirroring point on the other side are going to be 4 units away, and we should expect another point right here at negative 8, 7. And once we have that point, we can draw our parabola up through here and get a pretty good idea of what this parabola is going to look like. And fortunately, all of the other ancillary things that we would have anticipated or looked for came to pass. The fact that this A was positive means that the parabola opens up with which works out with all of the other points that we got. And again, we got the symmetry to work the way that we expected to. Sure, we knew the symmetry here. That was only because we were able to check it down here. We saw that those 2 points were the same distance from our ascertained axis of symmetry. Now, the one last thing before we end, we want to be very careful when we draw a parabola. I did not do a great job of drawing this as rounded as it should be. Remember, a parabola should have more of like a U feel to it than a V. So you should see this smooth roundedness into the bottom of the curve. There should not be any kind of harsh turns when you graph it. If you're still in the developmental stages of graphing a parabola, and that's perfectly fine, you're not going to sketch it perfectly every single time, but you wanted to see that rounded part at the bottom where you have a little bit more of that U shape. That's going to be really important when you get to pre-calculus and calculus, where there's going to be a distinction between shapes that are rounded at the bottom and shapes that come to hard corners at the bottom.